Welcome to this follow-up lecture on cardiac output methodologies. In this lecture, part B, we will have a look at non-invasive methods of determining cardiac outputs. My name is John Boland, and here we will look at 4 different non-invasive methods for cardiac output determination. Recap of our last lecture, we looked at invasive methodologies including the FIC, thermal dilution, energy pulse thermal dilution, and pulse pressure contour. In terms of what you need to know, considering that we're never likely to use some of the more complex involved ones used in theatres or ITU or ICU, it's enough to know that they exist and the basic mechanism of operation. But I encourage you to understand the physiology behind each. So you know the physiology behind pulse pressure contour. You know the physiology behind energy pulse thermal dilution, the vigilance. And you, of course, know the physiology behind FIC and indirect. The pulse pressure contour method, the device, is called PICO, and the names are useful in helping us to remember. As for non-invasive, there's ultrasound, and we won't go into that. You'll hear enough about that in your echo classes, except there is one other that I haven't included because it's not widely used in our lab, but it's out there. You should know about it, and it's called the USCOM. It's a handheld ultrasound device specifically to determine cardiac output. And if you're interested, I encourage you to read up on it, but I won't take up our lecture time talking about it. We look at partial rebreathing technique first. Carbon dioxide, partial rebreathing. First, we'll look at the advantages and disadvantages of ultrasound, particularly the transthoracic Doppler. It's non-invasive, transportable, can visualize cardiac structures very clearly, safe, repeatable. You don't need to be a doctor to do it. Stress echo obviously is possible and is accurate provided the baseline and the operators are correct. Disadvantage, expensive piece of equipment. You have to lug it around. You can't just transport it easily. Not for general use. You have to meet specific requirements to hook an echo. Requires a very high skill level, as you'll come to understand. Sterilization is essential for reusables, such as your toe probes. Subject to artifact, that's the biggest concern with echo. And cardiac output is not directly measured, it's estimated, and it can be technically difficult to measure linear blood velocity, which you will have a lot of fun learning how to do, if you haven't done so already. And we'll proceed with the cardiac output partial rebreathing technique. The device is known as the NICO. It's been around for a while, and it's a self-contained rebreathing circuit with various sensors and is attached to a patient via an endotracheal tube. So therein is its first serious limitation. We are unlikely to ever see it in the cath lab, not for us to use, because it's for dedicated use in intubated patients. The technique, and that's the important thing, is based on the principle that if you rebreathe your own exhaled air long enough, the partial pressure of carbon dioxide in alveolar air will equal the partial pressure of carbon dioxide in venous blood. Now that is a powerful little equilibrium point, and if you think about it, you'll understand why it is bound to happen. However, beyond a certain point, that equation or that balance will change for the worse for the patient. First, automatic baseline readings are taken with normal breathing over 1 minute. The patient then rebreathes part of previously exhaled carbon dioxide, not completely, just part of his rebreathed air is recirculated via a rebreathing loop for 50 seconds. This involves simply turning a tap on and off over a 50-second period. And this is followed by a further 70 seconds of non-rebreathing period, meaning breathing normally. Pulmonary capillary blood flow, meaning cardiac output, is calculated using the FIC principle. And instead of using oxygen as the indicator, here we're using CO2 as the indicator. And instead of using an arterial oxygen content, we're using VCO2 and arterial content of carbon dioxide. So carbon dioxide is the indicator instead of oxygen. And the machine follows and measures these changes during baseline and rebreathing periods. And one assumption the system makes is that the mixed venous CO2 and the dead space ventilation remain constant. The diagrams make the procedure a little bit easier to follow. Words are always cumbersome, but diagrams make it so much clearer. The patient is connected to his endotracheal tube and he breathes normally for at least 1 minute. And you can see we established the baseline values for VCO2, CO2 elimination as opposed to oxygen consumption, and end-tidal carbon dioxide. We then introduced the rebreathing cycle for 50 seconds, where a tap is turned and the patient partially rebreathes part of his own exhaled carbon dioxide. And as shown by the graphs, your VCO2 drops, your carbon dioxide elimination drops, as you would expect, it makes sense, and your end-tidal carbon dioxide increases. This just means that carbon dioxide accumulates in your lungs, in your system. And then you turn it off and you go back to a stabilization period of a further 70 seconds. And the machine does all the work. The advantages and disadvantages of the carbon dioxide partial rebreathing. It gives you a direct value. It's a continuous cardiac output monitor. It doesn't require a doctor once it's plugged in. It's a single operator use, independent of patient compliance. It's portable and it's low cost, and you get additional valuable respiratory information. Disadvantages: it has limited applications, so it's not a preferred option for many places. It's unpopular. It involves intubation. Not everybody's happy with that, but if a patient is already intubated, I don't understand the reason not to use a device like this. It's suitable mainly for ventilated patients. It's no information on oxygen uptake, unfortunately, and you can't exercise, but then an intubated patient, you're not likely to be concerned about exercising. Let's have a look at inert gas rebreathing, a product called the inner core. The main difference between inert gas rebreathing and carbon dioxide rebreathing is that, unlike the rebreathing technique where you rebreathe your own exhaled CO2, with inert gas rebreathing you breathe normally, but there are two additional gases included into your gas mixture that you're breathing in. And inert gas rebreathing involves rebreathing an inert blood-soluble gas along with an inert blood insoluble gas. The soluble gas is absorbed via the lungs and is cleared exponentially at a rate proportional to lung perfusion being the cardiac output. So the soluble gas is simply eliminated very quickly. The inert gas is recirculated but does not get absorbed. It is inert metabolically. The cardiac output can be calculated from the blood gas washout curve and the recirculation of the inert gas. Oxygen uptake can also be calculated. The novelty of this method is that instead of using a mass spectrometer to measure gases, a photoacoustic infrared light detector is used, and that is a major revolutionary step forward in technology to completely reduce the size and the cost of this instrumentation and making it available commercially. Again, a drawing simplifies things. It's a portable little device, just a little box with a mask attached or a mouthpiece that can be sealed and a bag connected to your gases. So your rebreathing gases pass in and out of this bag during the rebreathing period, and the normal circuit of blood flow continues as usual, except that you now have two gases. nitrous oxide, which is the absorbed gas that's cleared continuously, and the non-absorbable inert component, sulfur hexafluoride. Interesting choice. And that's all it is. Flick a button, off you go, and you get your cardiac output. So the advantages and disadvantages of the inner core device: it's portable, compact, non-invasive, continuous analysis is possible. This one is compatible with exercise, suitable for pediatric use. Patient can be conscious or sedated. It's simple use by a single operator, and no doctor is needed for operation. The disadvantages are that there's a delay to repeat. You have to wait for the system to stabilize and completely clear of any gases, and it's not received any great widespread use, although we did have it in our hospital and the clinicians were pleased to have it. Next non-invasive technology is thoracic electrical bioimpedance, called the BioZ.com. TEB measures the mechanical blood flow characteristics of the heart via external sensors to compute factors such as cardiac output. And by sensors, we mean giant ECG leads. You'll see a picture in the next slide. The system works by transmitting an alternating current through the chest. And this alternating current follows the path of least resistance, as you expect, which happens to be a conveniently placed aorta with a highly conductive moving fluid. And the baseline impedance to this current is recorded. Now, impedance is simply, in simplistic terms, resistance. It's a resistance to flow, but it's a little bit more specific than that. So having measured the resting impedance, the resting resistance, think as the aortic blood volume and velocity change with every heartbeat, there are corresponding changes in impedance, and these are detected and used to calculate various hemodynamic values, including stroke volume and cardiac output. Very clever little device, again, highly dependent on available technology. And again, we had this one in our lab. The ones we haven't had are those for intubated patients. Here's the device, just giant ECG cables connected at the level of the heart and at the level of the neck. You have your input AC current coming from this bottom button, and it tracks up the aorta. It follows the natural direction of the aorta, and the detectors, the receivers, are these gel electrodes on the neck. We need 4 of them, 2 on the neck and 2 on the chest. The single-use disposable for obvious reasons, as is almost everything in hospitals these days. But technically, you would think it would be possible to reuse them. But for legal reasons, ethical reasons, we never reuse them. And the biggest cost in this device is the reusable ECG electrodes. The advantages and disadvantages. It's non-invasive, single operator, portable, no MD needed, independent of patient compliance, single operation, very much like the previous ones, little boxes. It's continuous beat by beat data that is very useful. You know your cardiac output every single heartbeat, or it can average a group of beats, and it's relatively inexpensive. The disadvantages are there are restrictions of use, basically anything that affects the conduction through the aorta, such as aortic incompetence, competing flows of blood forward and back, and an intra-aortic balloon pump. A balloon placed in the aorta, as you can appreciate, would also restrict that impedance through the aorta. And it's unsuitable for some patients. For example, we found one patient we could not use it on because he had a bull neck. Simply not enough space between the ear and the shoulders to locate the electrodes. Now that covers our non-invasive technology, and I'm pleased we split the lectures into 2. This has taken a full-length lecture, but the big choice any doctor has to make who wants a cardiac output is deciding on the methodology he prefers to use. First, is likely to be invasive or non-invasive? What are the circumstances? Is it a hospital? Is it a clinic? What facilities are available? Do you use a FIC or a thermal dilution? Same question. What resources do you have? Do you require a continuous cardiac output? That eliminates a few options. And are you going to use it on intubated or routine patients? There are many papers written just on this very topic. How do you choose what device? The impetus these days is favoring non-invasive. So there's a big push to find a suitable non-invasive cardiac output measurement that, if not as accurate as FIC, the direct FIC, for example, or even thermal dilution, is at least accurate enough to suit the needs at the time and for the patient and for the doctor. And there's always the issue of whether you need to exercise a patient or not. Many cardiovascular pathologies appear normal at rest and only flag up on exercise when the heart is challenged to perform. I hope you've enjoyed and appreciated these series of lectures. I know they've been complex and for many of you novices may be challenging, but once you read a little bit about it, they're not that difficult. As usual, you have some reading material that is intended to facilitate your understanding of this topic. But on that note, we will end this lecture.